Alright, so this is your energy introduction. We'll certainly have to have more conversations after this, but let's just get you started with the types of energy. So the different types of energy you're going to look at first are kinetic energy. Kinetic energy is 1/2 mv squared. You'll notice that since it's v squared, v squared can never be negative, so kinetic energy is always a positive quantity. We'll have potential energy, and specifically this is the gravitational potential energy, which is equal to mgh. And then we have elastic, which is a different type of potential energy, but elastic energy is like the energy stored in a rubber band or in a bungee cord or in a spring, anything that really can stretch or compress. And so this is how you find out the energy. The amount of energy is in joules. Okay, that's the unit of energy. But then we also have this concept of work. And it's almost semantics of what's energy and what's work. Work is what you do to an object, and then energy is what it possesses. So realistically, you could take a ball and you could do work on it, and then it would give it kinetic energy. You could take a spring and you would stretch the spring. You would do work, and well, that work would equal the energy that it would then store. And so energy is kind of what some object maybe possesses, and work is kind of what you do. Work is really easy if the force is constant. So work equals F times displacement, and really that's a dot product, and we'll discuss that later, because those things need to be in the same direction. Again, we'll discuss the dot product later. If the force isn't constant, well then we have to accumulate the force over distance, and so we end up getting an integral. Okay? And then we also can use the work energy theorem and say that the work is really equivalent to the change in kinetic energy. And hopefully that makes sense. If you apply a force, which is an acceleration, over a distance, you get a change in velocity, thus a change in kinetic energy. And you're going to use all these things in a row. And what we're going to do sometimes is we're going to look at the work done by friction. Well, if the work done by friction, as long as the frictional force is constant, which most of the time it is, and the work done by friction is just the force of friction times the distance. Don't forget that distance. Again, there's a difference between the work done by friction and then the force of friction. And so when you're in an energy and work situation, you want to use the work done by friction. Okay? And the friction, sometimes it's referred to as heat. Sometimes they call it thermal energy, or even internal energy. Okay? All those three words just mean that energy is going to be lost to the system in terms of usable energy. Energy is not lost, but mechanical energy. These things would be mechanical energy, and this would be kind of waste energy. It just gets dissipated in the environment. Okay, so this is kind of the foundation for energy. There's lots of other things that we need to discuss, but let's just get started, and we'll just do some sample problems, and that'll get you enough to kind of get you started on Monday with the worksheet. So let's just take a ball, and let's just throw it in the air. Okay, and let's say the mass is 4 kilograms, and we give it some initial velocity of 15 meters per second. Okay, and then the question is just how high does it go? And instead of looking at it from a kinematics point of view, using maybe like the v squared equation or acceleration due to gravity, we're just going to use conservation of energy. And so what we're going to say is that the energy at the beginning equals the energy at the end. The energy at the beginning is all kinetic energy, and at the very, very top, well, it's all potential energy. The kinetic energy is just 1/2 mv squared, and the potential energy is just mgh. Again, this is the amount of energy you gave it at the beginning, so you must have done some work to throw this thing and give it some velocity. But after you get done throwing it, it has a velocity, so that's the amount of energy it has. And all of that energy just transfers, it's converted to gravitational potential energy, because at the top, it stopped. And so if you plug in the numbers at this point, you have 1/2 times 4 times 15 squared equals 4 times 9.8 h. And you're going to find that the h is equal to 11.48 meters. Again, at the very, very top, it's got the same amount of energy that it had at the bottom. Okay, so we just conserve energy. Again, this here is going to be the key argument that you use on almost every single problem. Okay, let's take a slightly different one. Okay, let's take a ramp, and we've done ramps before. Okay, let's give it a certain angle, give it a certain coefficient of friction, let's give it a certain height, Let's put a mass on here and let's just let it slide down. But this time, though, we're going to use energy instead of forces to find the velocity. If you use forces, we typically would have found the acceleration. So if we would have found forces, we can analyze it using F equals ma, and then with A, we could use like, oh, maybe the v squared equation to find the final velocity. So instead of doing it this way, let's use energy, okay? And we want to find the velocity at the bottom. We'll call that v final. Okay, and realistically what we're going to do is we're just going to do the same thing. The energy at the top gets converted to energy at the bottom. What type of energy does it have at the top? Well, it's not moving, and so it probably just has some potential energy, right? However, it's going to lose energy due to heat, right? When this box slides on here, with the work done by friction is going to be the force of friction times distance. So we need to take that away, and all of that left over then is going to convert to kinetic. Okay? So we don't lose energy per se, but we do lose mechanical energy. We lose useful energy. So the potential energy is just mgh. The work done by friction is the force of friction times the distance, and then all that left over goes into kinetic energy. Okay? So let's say we have a height of 3 meters. So let's say this is 3 meters. Let's say this is 2 kilograms. The coefficient of friction is 0.25. Let's say the angle is 60 degrees. Okay, and one of the more challenging parts here is to somehow relate h to d. They're not going to give you both of those things, but they really did. If you really think about it here, we have this picture. This angle is 60 degrees. If this is 3 meters, and this is 60 degrees, then what is d? Because the force of friction acts on this distance. So the ramp distance is the important part when you're looking at the work done by friction, where potential energy is all based on height. And so if you think about that, sine theta is going to be 3 over d, then d equals 3 over sine theta. Okay? And that equals what, 3.46? And so at this point we know everything in this equation. So 2 times 9.8 times 3 minus, what's the force of friction? Well, the force of friction, go back old school, is mu mg cosine theta times our d of 3.46 equals 1/2 times 4 times v squared. Again, this is the force of friction times the distance gives you the work done by friction. That's the energy that is stolen here. And then you do get a final velocity then of 7.09 meters per second. And I would challenge you to do the exact same thing over here, and it would be fine. You still have to find the acceleration using an entire force analysis, you know, mg sine theta minus mu mg cosine theta equals ma, right? Starting out with F equals ma in a free body diagram, and that leads you to the acceleration, and the acceleration will lead to the velocity. Okay? So again, conservation of energy. Here we didn't have any drag forces or any friction or anything, so we just set the energy at the bottom equal to the energy at the top. Here, we set the energies equal, but we do have to take away some from the initial energy. Not all of the potential energy converts to kinetic at the bottom. Okay? So we'll just continue on through. We'll just keep doing a different example this time. We will get a spring involved. And so this time, let's do a ball ramp and a spring. So let's kind of take this picture, and we're going to put a spring on the end of this. Okay, so let's take a ball, it's going to roll down this ramp, and then hit this spring. Okay, so on this one we'll say no friction. No friction, so we're not going to lose any energy. Okay, and so realistically there's kind of like 3 points here. There's the ball at the top, we'll call that E1. There's the energy it has before it hits the spring, and then there's the energy it has when it fully compresses the spring. Well, all of those energies really are the same. There's no loss of energy anywhere. The energy at the beginning is all gravitational potential. At the bottom, before it hits the ramp, it's all kinetic. And then when it hits the spring and compresses it fully, well, eventually it's going to compress it to its maximum value, and the ball's going to stop. And so then all the energy then is elastic. And so what we really can say here is that mgh must equal 1/2 mv squared, which then also equals 1/2 kx squared. Again, this 1/2 kx squared is going to be used for probably 95, 98% of all the springs. Okay, there's going to be springs that don't follow this, and again, we'll discuss Hooke's law at length at another time. But if we don't say anything in the problem, assume that it's a Hooke's law spring, and then 1/2 kx squared describes its energy. Okay, and so over here we say, well, let's just drop it from 5 meters. Let's let the ball be 3 kilograms. And K, well, what's this K? Well, K is going to end up being the spring constant. The spring constant is the stiffness of the spring. Okay? And again, it's a brief discussion that the 1/2 kx squared comes from Hooke's law. Hooke's law just says this. F equals negative kx. And it's not really that difficult. It just says that the force of a spring, its opposite, some spring constant, times x. Well, of course it's opposite. If you take a rubber band and you move it to the right, the force is going to be to the left. If you take a spring and you compress it left, well, then the force is going to be to the right. The force is always opposite of the direction of the displacement. X is the displacement from equilibrium. Okay? So example, if you have an original length of, let's say, 10 centimeters, and you stretch it then to 12 centimeters, X is only going to be 2 centimeters. Again, it's how much it's actually stretched. It doesn't really matter the length of the spring per se, it's how much you've compressed it or stretched it. And K is in newtons per meter. It's basically saying how hard it is in a force to stretch it every single meter. Okay? And so that's where this K comes in. And so when you have all these values, so it's 3 times 9.8 dropped from 5 equals 1/2 times 3 times v squared. And then you can solve for the velocity at the bottom of this thing. That's going to be somewhere around 9.9 meters per second. And then you do the whole thing over again. Again, you can either use this is equal to this, or this is equal to this, because really all three of them are equal. I think that's like the transitive property in geometry. It's no big deal. Whatever you want to do. So down here you can do another problem where it says, just take the original MGH and then say that we never even care about the velocity here. We'll take the energy at the beginning and choom, the energy stored at the end. And when you plug in there, hopefully you get an X value of, I think my handwriting says 0.24 meters. And again, that's how far it would be compressed. Okay, and all we did was conserve energy. Okay, next problem, let's look at the work energy. And again, if you remember, the work energy, again, looking back at our types of energy, the work energy theorem is right here. It says that the work done is equal to the change in kinetic energy. It's key that it's the change in kinetic energy. Okay? And so when we look at that right now, let's just take a car and let's just accelerate it. Okay, and let's talk about the energy that is required to do that. So let's take an 800 kilogram car, which is probably somewhere typical. Let's have it at rest at the beginning. And then let's accelerate it. Okay, let's accelerate it to, we'll call it V1 of 10 meters per second. Okay, and let's figure out the work done. So the work done is going to equal the change in kinetic energy. The change in kinetic energy is just the kinetic final minus the kinetic initial. And again, that's the definition of the change in something. It's always the final minus the initial. The initial happened to be 0, so the work done then is just 1/2 times m, which is 800, times 10. Okay, and that should give you 40,000 joules. Again, so if you take your car on the road, assuming no drag force and no loss of energy due to friction, just the energy required, meaning the work required for your engine to accelerate it from 0 to 10 is 40,000 joules. An interesting question then is what would happen then for the work required to go to V2, and V2 is 20 meters per second. And again, this is kind of a tricky one if you think about it at first. Some people might be saying, well, to go from 0 to 10 took 40,000. Does it take the same amount of energy to go from 10 to 20? And that's a question you want to think about. The key here is to realize that kinetic energy is proportional to v squared. Okay, not v, there's not a delta v here, there's a v squared. So for going from 0 to 10 is much different than going from 10 to 20, and here's why. Think about the kinetic energy here. So the work required on the second phase is going to still be, one is going to be kinetic final minus kinetic initial, and we're looking at the work to go from 10 to 20, so it's going to be 1/2 times 800 times 20 squared minus 1/2 times 800 times 10 squared. Well, 20 squared is 400. This is going to be 100, so that's 300 times 1/2 times 80, and that's going to be 120,000. Hopefully you can see 3 times the amount of energy, and again, that's in joules. Work and energy are always in joules. Work is what you do, energy is then what it possesses. Again, 3 times the amount of energy required to take something from 10 to 20. So when you're on the highway, it's much, much more difficult for your car to accelerate, let's say, from 65 miles an hour to 70 miles an hour than it is to go from like 10 to 15. It takes almost no energy at the very beginning when your velocities are small to increase. So like starting up your car and passing someone at a small speed, piece of cake. Passing someone at a very high velocity, much different, much more energy required to be able to do that. And the same reason for your brakes, much more difficult for your brakes to work because they have to absorb all that energy going at really high speeds than going at low speeds. Okay, so that's kind of our work energy example. Okay, let's take a pendulum here. Okay, so let's have this fixed top here, and we'll put a ball on the end of a string, and we'll let it rotate down. There's a certain length, it's got a certain mass, and of course it's going to be displaced a certain angle from equilibrium. And so let's just release it. We're going to release it and it's going to come down, and we're going to figure out, well, what's its maximum velocity? Well, the energy at the top is still going to equal the energy at the bottom. No energy is lost due to the work done by friction or any drag forces. Okay, let's say that the mass is a 2 kilogram ball, the length of the string is 4 meters, and let's say the original angle was 70 degrees. Okay, and so, well, the energy is just, at the beginning it has mgh, and at the end it's got 1/2 mv squared. And again, this h, we're going to discuss this, more and more and more. This h is really a delta h. It all matters about the change in height. So where is your reference point? Well, your reference point of what a 0 is just going to be at the bottom of this swing. Why not make that line your y equals 0 line? I mean, who cares if this is actually the ground? I mean, the ground could be way down here. Who cares? And we'll show that in a roller coaster example coming up. But we're going to make this the reference point of y equals 0. It's the lowest point. I make it there because if we make that y equals 0, then the energy at that point doesn't involve any potential energy. There's no mgh on this side if we make this y equals 0. And so this h is this distance. And that's really the key here. How do you find that distance? So if that's L, and then it swings down here, and then that's also L, the question is, what's this little h? This little h goes from there to there. Well, think about a little geometry here. If that's theta, this distance from here to here, if this distance is L, this is L cosine theta. But from here to here is full L. Do you see this little height change then is going to be L minus L cosine theta? And so then we have mg times L minus L cosine theta equals 1/2 mv squared. And again, you can actually even show that the masses don't even matter. It's all about the height. It's really all about the change in the height. Right? That's how much height you lost. That loss of height is going to transfer over to here. And so when you plug those in, you should get a maximum velocity of 7.18. And then again, just in meters per second. Okay? If you plugged it in over here, you should have gotten a height of 2.63. That was the loss of height. Okay? Okay, let's drop, this one gets kind of hard sometimes. Let's drop a ball onto a spring. So let's take a mass, and we'll drop it, and it's going to go to a spring. Okay, here is the ground, and here is my spring. Okay, h is going to represent the distance the ball is to the top of the spring. X, of course, represents how much the spring compresses. Okay, so the question is, well, we're still going to conserve energy. What energy does it have at the beginning? Well, it has mgh. However, we don't want to use the ground as y equals 0, because I don't even know what this height is right here. We're going to use this dotted line as our y equals 0. If you think about it, when the ball gets fully compressed, or when the spring, gets fully compressed from the ball, we want that to represent y equals 0, because then at that moment, all the energy is only in one type. It's all inelastic. So at the beginning, mg, it's actually at a distance h plus x up. It's h above the top of the spring, but then the spring is going to compress another distance x. So how far the ball actually starts up is h plus x. At the end, there's no kinetic because the ball stopped. There's no more potential because the ball has reached our y equals 0 point, and so then all the energy is stored in elastic. Okay? And so if you look at some numbers here, if we drop it from 8 meters, and the ball is 2 kilograms, and let's just go ahead and take a spring constant of 3,600 Newton meters. Okay, we want to figure out how much is it going to compress the spring. And so when you use these values here, you should then get an x of 0.3 meters, so 30 centimeters. Okay? Again, K is the stiffness of the spring. We're going to transfer all of this gravitational potential energy, mgh, fall down here. And now during this path, does it become kinetic? Sure. If we were interested in the velocity. Well, what if we were interested in the velocity right before it struck the spring? Well, we'd still conserve energy. The energy now would just be mgh, because if we're interested in the velocity here, it would only be the height we've actually fallen. The spring isn't compressed at all, and so that change in height would then be equal to 1/2 mv squared. Okay? Cancel the masses, multiply by this, and you get v equals the square root of 2gh. And if you think about it, isn't that exactly the same thing if you look at our v squared equation that we used to do? If the initial velocity was 0, isn't the velocity the square root of 2ax, where x is the same thing as h, and acceleration is gravity. And so energy is the same thing as what we used to use for the v squared equation. Again, you just have to pick and choose what you want. Certainly, potential becomes kinetic, and then kinetic and potential all transfer to elastic. If you're only interested in elastic, just go from the very beginning of the motion to the very end. Okay? And let's just do one more problem. Okay? The last problem is going to involve just a roller coaster. Okay? And so the roller coaster, problem might look something like this. And it's going to drop in and maybe have a hump. And then let's say it just goes down to 0. Okay? So let's call this point A, at point B, and at the end, point C. Okay? So let's say this is H1 and H2. Okay? So we want to find all these things. And I really just want to show you how it's all about the change in height. And so if there's no loss of energy, then the energy at A equals the energy at B, which equals the energy at C. All those energies are the same. Okay? Let's say there's no initial velocity. Okay? So now if we look at the energy of A, so let's just look at this first part here. The energy at A is mgh1, no kinetic energy at A. And at B, what still has a height, mgh2, but then it's going to have 1/2 mvb squared, the velocity at point B. Okay, but if you subtract here, aren't you really going to say mgh1 minus mgh2 equals 1/2 mvb squared? And can't you factor out that h and really, or mg, excuse me, and say that h1 minus h2 equals 1/2 mvb squared? And isn't that really just delta H? So isn't it really the loss of potential energy gets converted to kinetic? Who really cares if it's at 500 meters? It's all about how much it's lost. I mean, if I take a ball and I drop it, all that matters is that it loses 10 meters. It can go from 10 meters to 0 meters, or it could go from 500 meters, we're on some mountain, and we drop it to 490 meters. The actual height of the ball is completely irrelevant. It's all about the loss of height. It's all about delta H. Again, just reminding you that this H is completely all based on a reference point. We just called this 0. We could have called this 0. And then right away with this H1 would have been H1 minus H2. Okay? And at C, well, you can go all the way back from the beginning. Then it is just 1/2 mv squared because C doesn't have any height. And again, I really want to reinforce the fact that the H in MGH is all about a delta H. It's all about how much height you're losing or how much height you're gaining. Okay? So if you think about all those problems again, I'm going to pull them back up here. Here's where we started. We started out really looking at different types of energy. The different types of energy. We had kinetic energy, which is always positive. We have potential energy. Now, we didn't do any examples where potential energy ends up being a negative, but if we put a reference point somewhere higher than the final position, you would end up having a potential energy of negative. Elastic is always a positive because you're squaring the x. X represents the displacement, either compression or stretch. K is the spring constant, which is like the stiffness of the spring. We did work. Work in the very easy cases is FD. Well, that's only true. You're going to make a note to yourself. Go back to your notes. This is only true is if F is constant. The easiest example is the work done by friction. It's just the force of friction times D, where the force of friction is usually not dependent on X. If it is dependent on X, like a spring is, then we have to integrate F dx. We also can say that the work done is equal to the change in kinetic energy. Okay? So we took a ball and we threw it in the air. It had kinetic, it went to potential, we set them equal to each other. We had a box on a ramp that had potential energy at the beginning. It slid down, it lost some due to friction. Again, not the force of friction, the work done by friction, and the rest of that was converted into kinetic. We looked at a ball sliding down a ramp and hitting a spring. Again, there's all sorts of energy transfers there. We had some potential, it gains to kinetic, and at the bottom it's all kinetic. And then all that kinetic compresses the spring and turns it into elastic. You just conserve energy in that case. We had the pendulum. Pendulum ends up being pretty easy. It doesn't matter if it's a pendulum or it's a ramp. It starts out with potential energy and then it became kinetic. We made the bottom reference point y equals 0, so that made that there was no potential energy here, so it was just mgh equals 1/2 mv squared. Do a little bit of geometry to relate the angle in L to h. Okay? We can drop a ball onto a spring. You just got to be careful that when it compresses the distance x, it also increases the total height it fell. It fell h, but then also it fell x when it compressed the spring. And then again, we looked at the roller coaster example, and I don't think I missed any looking back through the sheets. But again, it's one of those things that it's all about the change in height here. Okay? This should be enough to get you started doing the energy sheet. So there'll be maybe a couple other cool videos I want them to show you, but this should generally get you started. I'm going to have her pass out the energy sheet on Monday. You should have plenty of time to go through the 8 problems. They're similar to this. Hopefully you took notes. If not, you can rewatch it either on Saturday or Sunday to kind of review for Monday. But when I get back on Tuesday, it should be totally fine. We'll look at work energy. We'll look at things where springs aren't 1/2 kx squared. I'll derive using calculus and geometry to show you where that 1/2 kx squared comes from. We'll discuss the idea of power, which is doing work per second. So lots of other things we have to do, but I think you should be okay on Monday. Enjoy your weekend.